Welcome to Unit 10, Introduction to Calculus. It's B again, and our first lesson in this unit is an introduction to limits. When you're putting together a jigsaw puzzle and are looking for a specific piece, what do you do to find it? Do you just start grabbing pieces at random, or do you look at the surrounding pieces to narrow down which piece would fit? The idea of using the known surrounding pieces to determine a missing piece is exactly what we're doing today with limits. We'll be filling in the blanks of a function by looking at what's nearby. So let's fit the pieces into place and reveal the big picture behind limits. Today's warm-up on the first page of your lesson materials may not seem like it relates to precalculus, but let's take a closer look. If you haven't already, pause the video to draw what you think the missing puzzle piece looks like. What did your piece look like? Mine was one of these two. Which one do you think it was? Right, it was this one. But how did you know that? By looking at the surrounding pieces. The piece on the top, the one with the spikes on the dinosaur's back, wouldn't make sense in the context of the larger picture, would it? Here's another question. What if I had asked you to draw that same puzzle piece, but removed all of these surrounding pieces? Would it have been harder to figure out what the gray piece looks like? Why? Take a moment to record your thoughts in your guided notes. What did you come up with? I was noticing that it's harder to draw the missing piece when the surrounding pieces are gone because you don't have much to work with. There's no context to guide your guess. We can't see the shape of the dinosaur's back, or whether it has spikes or a shell. But when the surrounding pieces are there, it's easier to make an accurate prediction because you can see how the missing piece connects to the larger picture. The more information we have, the more confident we can be about what fits. This puzzle exercise might seem simple, but it illustrates an important idea for today's lesson on limits. Just as surrounding puzzle pieces help us infer the missing one, we can use nearby values to understand a function's behavior. Let's take a look at an example. Given this function f of x, find f of 1. Take a moment and do some mental math. Did you get stuck in the same place I did? When I substitute 1 for x, I get 0 over 0, which is undefined. So we can't actually find f of 1. But what if we wanted to estimate a value for f of 1 that would make sense with the rest of the function? Maybe we could evaluate some other values of x and look for patterns. What about using these x values? I have 2 values smaller than 1 and 2 values larger. Maybe that will help me determine a pattern. The associated y values to complete this table are here. I could do some algebra and try to find a pattern, but the table as it is now is kind of like our puzzle with these outer pieces missing. It's a little tough to fill in a value for f of 1 without having more information. What could we do? Well, kind of like filling in more of our puzzle, what if we choose x values that are closer to 1? Pause your video here and fill in the function values for this table. Feel free to use a calculator if you'd like. Here are the function values I found. Kind of like a missing puzzle piece. Even though we still can't evaluate directly for f of 1, we can see that if we follow the pattern evident in the table, as x approaches 1, the function seems to be approaching 2. Like the function we just saw, there are a lot of times in the real world where we can't calculate a value directly, but we can see what it should be as we get closer and closer to it. Mathematicians call this the limit of a function, and in fact, it's the idea that all of calculus is based on. In math, new definitions often need new notation too. Let's take a look at limit notations as we develop an intuitive sense for its definition. The notation you see on your screen is read as the limit of f of x as x approaches a is L. Let's look closer at the notation. We use the abbreviation LIM for limit. Below LIM, we write the independent variable, which is usually x, with an arrow pointing to the x value at which we want to find the limit. Here we can either use the function's name in function notation, or we could insert a specific function. Finally, the equal sign and the L show what the limit actually is. We can also say it this way. The limit of a function at a is the value L that the function approaches as x gets closer to a. Let's make this a bit more concrete by jumping back to our most recent example. We could rephrase the question in limit notation. What is the limit of f of x as x approaches 1? We already know from the table that the function values are approaching 2, so we would say that the limit of f of x as x approaches, or goes to 1, is 2. Let's try an example. Find the limit of g of x as x approaches -3. Before we dive in, note a key concept of limits. The limit describes the behavior of the function near a, not necessarily the function value at a. This gray box is preventing us from seeing the function's value at -3. But can we say something about the function's behavior near -3? What do you think the limit is? Based on the portion of the function we can see, I would probably estimate the limit to be something close to 1/2, or maybe 1-ish. But there's a lot of function hiding behind the gray box. What if we were able to see more of it? Do you still think the limit might be 1/2? I'm still not quite sure what the limit is at -3, but I definitely don't think it's 1/2. Maybe it's 2? Well, let's get even closer to -3. Now we can see more of the function, and it becomes clear that g of x is increasing very quickly. In this situation, we would actually say that the limit of g of x as x approaches -3 is infinity. We will look at special cases like infinity and how limits relate to asymptotes later in this unit, but this example illustrates another key concept. To accurately find a limit, we need to look at x values that are very close to a. In other words, really close. So close that they're practically brushing right up against a, but not actually reaching it. To wrap up today's introductory lesson, let's practice identifying a few basic limits. Pause your video and use your guided notes to determine the following limits for f of x using the table or g of x using the graph. How did you do? Let's take a look at each one. First, find the limit of f of x as x approaches, or goes to, -3. Looking at the table, we don't know whether f is defined at -3, but we can see x values that are pretty close to -3. That means we can look at the y values to see whether the function seems to be approaching any specific value. In this case, we can say that the limit of f of x as x approaches -3 is 12. Now, let's look at the graph of g of x. Let's see what the function is approaching as x approaches -3. Here, the limit is straightforward. As the x values approach -3, we see that y gets closer to -6, and the limit is -6. Finally, what value is g of x approaching as x approaches -1? The hole at x equals -1 is similar to our earlier example where the gray boxes hid the function value. Even though g of x isn't defined at -1, the y values on both sides approach 8. So, the limit of g of x as x approaches -1 is 8. Great work! Here are our key takeaways for today. The limit describes how the y values of a function behave as the x values get closer and closer to a value a. We say the limit of f of x as x approaches a is L, and to express that succinctly, we use limit notation. Remember, the function value at a may be undefined or unknown, but the key is to determine what the function approaches as x gets closer to a. Now that you've finished this video and your guided notes, check out the rest of the lesson activities and the online practice. Be sure to join me next time when we deepen our understanding of the limit and find limits from just one side of a given x value. See you then!
Hey, hey.